Okay. Thank you everyone for being here. I know it's been an exhausting 2 weeks, but to close off this 2-week workshop, we have Chethan, who's going to finally solve the mystery of dark matter for us. So thank you, Chethan.
Thanks for the invitation. And so my talk is not so much going to be ADS-CFT. I hope that you're probably a little bit sick and tired of it by now. Maybe not. I'm sure you're not. But part of the reason I decided to talk about this was because a lot of the people who were supposed to be in the audience had heard my previous talks on ADS-CFT, which were like from the recent work that I did. So it turns out that none of them are here now, but I'm stuck with this talk anyway. So this is some work that I've been doing with Ranit, who is at the back, and it's in many ways it's very elementary, and it's just mostly just a comment in some sense, and so it's not yet out. So if there is some comments that you have, and if it is wrong, you can tell me, and maybe we will not put out the paper. So this is kind of a trial run. Okay. Anyways. So that's so much for the introduction, and let's start. So the basic idea behind dark matter energy is that there is a tremendous amount of evidence at this point from many different scales, starting from, let's say, subgalactic to all the way up to cosmological scales, where there is a lot of independent evidence for the presence of some hidden stress tensor in the universe. And at this point, I would say that there is no question at all that it is a fact that there is a missing energy momentum tensor in the universe, and that's what we call dark matter energy. And the basic conclusion is that there's only 5% of the stress tensor is visible matter, and it behooves us to try and explain what this extra stuff is. So there is a lot to be said here, and I'm far from an expert on this, but so let me say a few words which are probably sort of introductory for some of you, and probably maybe too familiar for some others. So in any event, so the point about this is that above galactic scales, so most of this dark matter energy that you find can be explained in terms of by just postulating that the stress tensor that you have is a pressureless dust plus some dark energy. So dark energy is it's again a perfect fluid, and this is basically the lambda CDM model, and it does a good job of explaining cosmological data that we get from satellite WMAP. So this success, one of the things I would like to kind of emphasize, that this success does not really require detailed models of dark matter energy. So what it really captures, even structure formation, which is usually done through intense simulations on computers, what you generally assume is that you start with some collisionless particles, which are models for dark matter, a dust basically. Dark matter is basically just dust, which means that there's no pressure, there's no interaction. So you basically run that through cosmological timescales, and then you find that structure forms as we kind of expect. There are some mismatches here and there, but overall it sort of works. So the basic point that I want to take away from that is that a lot of it actually just requires the presence of the stress tensor. Okay, so, and that's the one thing that I want to kind of emphasize. And any theory that can, in some sense, reproduce the stress tensor is largely on the same observational footing as lambda CDM. So, and there is a lot of models for it. There is a lot of models for what exactly this dark matter is. But I think there are more or less well-motivated models of various kinds. But this statement, I believe, is true in the sense that if we can explain the stress tensor, most of them basically what they do is try and explain the stress tensor. Yeah, so as I mentioned, there are many distinct pieces of evidence for dark matter at all astrophysical and cosmological scales, but all of this evidence so far is gravitational. Okay, so in other words, it should really be emphasized that all of the evidence that we know for it is coming from a missing stress tensor piece in the Einstein equation. So if we can somehow manage to explain that in one way or another, we are sort of done. So the underlying theory model behind the stress tensor is mostly not yet observationally accessible, and one of the ways in which we try to get access to that is by making direct detection experiments, for example. And there is a lot of contradictory data in that department, but I don't think there is any. I think it is safe to say that there is consensus that an actual confirmed direct detection has been made yet. So that's a status. And so when you have something like dark matter is basically just a statement that there is a gravitational discrepancy in astronomy or cosmology. And one way to go about when you have that is to postulate missing matter, the obvious way to do that. and the other is to modify the theory of gravity. And both of these have, as you probably well know, have historical precedences. The first one was, most of the exoplanets were discovered through the dark matter hypothesis of one form or another applied to Newtonian gravity. And so in the case of Mercury's perihelion, Einstein's theory came along as a way of, so there was a postulated inner planet, but it turned out that Einstein's theory was actually the right theory, and within the theory itself, you didn't need any extra matter to explain the perihelion shift of Mercury. So all of these are historical facts which kind of correspond to various attempts that are going on now to explain dark matter in various ways. So the current majority view is that this missing matter should be viewed as arising from some dark matter of some kind, which is, for example, let's say the light of supersymmetric particle, which is some weakly interacting massive particle, or in maybe I would say that at the moment maybe axions are looking more promising as dark matter candidates. So that's a whole different thing. I don't want to talk about it, but so there are many other candidates for this, and you also have this issue that the lambda CDM model that I talked about at subgalactic scales, especially near the cores of galaxies, it runs into trouble. Because there is this prediction that lambda CDM makes, which is that you have a cusp at the center, but instead what you actually find is obviously something more like a core. So that is not something that lambda CDM is not at the moment able to explain. So one of the ways in which it can be possibly gotten behind is by versions of axionic dark matter. I'm not an expert on this, but this is what I understand. So this is the standard paradigm in some sense. This is a paradigm for dark matter. And the general belief or the general suspicion is that gravity modification is definitely not a viable candidate for doing anything with dark matter. There are multiple reasons for it. I'll mention some of them as we go along. So let me start by saying what I'm planning to do, which is basically an attempt at something of the kind which is halfway between matter and halfway between gravity, let's say. And so the idea is that we'll argue that a background non-Riemannian piece in the affine connection, which defines covariant derivatives on fields, looks exactly like a stress tensor piece at the level of the field equations. This is the basic observation. And it's not very clear to me whether it has been it's a very trivial, almost trivial fact, as you will see the entire of this part of the thing I can put on the slide because it's trivial, but it doesn't seem to me that this has really, even that fact has really been appreciated at the level of the equations of motion. So maybe I'm just not Googling hard enough, but this seems to be the case. So this is one basic observation that we'll make. But of course, if you modify the connection in general relativity, you run into all kinds of trouble. You could potentially run into all kinds of trouble having to do with the fact that you might violate the equivalence principle and all the tests of general relativity and so on. So we have to worry about that. Maybe that's the reason why people have not investigated it in the past. I don't know. But we'll argue that there is a sense in which it seems eminently plausible to me that it will not really be a problem as far as the tests of general relativity are considered. So I'll explain why as we go along. So this is a small comment, which is that there is the same paradigm will actually give us the possibility of scattering of anything higher than, let's say, a vector field, anything higher than scalars and gauge fields can scatter off of this background connection, which can in principle look like dark matter direct detection scattering type of experiments. So that's the basic story. So moving on. So the dark stress tensor in this picture is algebraically determined in terms of the dark connection. I'll explain what the dark connection precisely is. And it is easily seen that it is possible to choose it so that it reproduces the lambda CDM or galactic dark matter. So one thing I want to emphasize, that I'm just stating this as a possible paradigm. I meant what I said in the title, which is that it is kind of a scenario where it seems like maybe there is something that can be explored. I'm definitely not offering a specific theory which gives us the lambda CDM stress tensor. I'm just saying that if you choose the connection in some particular way, and if you choose the background connection is, I'll explain why it's meaningful to give it a background value, because you might worry that it's a connection, not a tensor and so on. But yeah, so if you give it if you give it a background value for the connection, I will claim that it can be algebraically related to the stress tensor, and by choosing appropriate values for it, you will be able to reproduce pretty much anything, not pretty much anything. So the kind of perfect fluids that are useful for dark sector model building both in inside galaxies and outside. So yeah, so that's basically our basic setup. And yeah, so this is something that I wanted to emphasize, which is that we are not going to really try and write down a microscopic theory for the dark connection. So you might, in some sense, you're just transferring the problem of understanding dark matter to what exactly is the theory for the dark connection. But I still think that it's a little bit coming from the left field compared to the standard approaches to dark matter. So if it is right. So yeah, so it seems surprising to me that it is not ruled out as far as I can tell. So why are we doing this? So why are we doing this? So one of my main motivation in looking at this question was primarily because there is this general, I wanted to understand how much is gravity modification really ruled out? Because there is this general statement that one hears, which is that because of bullet cluster and dark matterless galaxies and so on, there is strong evidence at this point that gravity modification just cannot do anything as far as dark matter is considered. And I think that's too broad a statement, I think. And the reason why it's too broad a statement is because if general relativity automatically comes with two fields, one is a metric and one is a connection, and it's a dynamical fact about general relativity that the connection gets determined in terms of the metric. And so at least there is automatically in the theory, there is a sense in which there are two fields. So possibly, if you give the possibility of, if you allow the possibility of having more than one field in the theory, one of them can act a little bit like matter. That's roughly the idea here. So will I go back? Yeah. So the idea, so the question of what qualifies as gravity and what qualifies as matter in this picture is a little bit fuzzy. So, and that's where we are kind of able to sort of get out of this folk no-go theorems, let's say, which forbid the existence of gravity modification. So, yeah, so the idea is that we can simulate the stress tensor using this dark connection. And so because of which the evidence that we have for various things, these things which otherwise would be really hard to explain in any kind of gravity modification, we can manage. So the idea is, if you have not heard of the bullet cluster, it's basically two galaxies or clusters that just pass through each other. And the point is that gravitational lensing around it tells you that there is some hidden matter that just kept going. So you can really see that if the only assumption that goes into the statement that bullet cluster really shows that dark matter exists is the only assumption really is that gravity is coming from the source. That's really the only assumption, I would say. There is not even the assumption of general relativity, none of that thing. So if gravity is coming from where matter is, then bullet cluster is really telling us that there has to be matter somewhere we are not seeing it. Okay, so that's a pretty strong argument against gravity modification, which I think any gravity modification theory should have to address. So, but in our case, we'll get past that because connection is really like matter. So even though it is superficially part of gravity, it is somehow like matter. So in principle, the connection, as long as it is a field in the theory, it can act as matter, and so we can get out of this. So, and dark matterless galaxies are this. So this another thing, which is that if gravity comes automatically with the modification built in, like gravity is only one gravity, so which means that if you have dark matterless, there cannot be such a thing as dark matterless galaxies if gravity modification is the way in which dark matter is implemented in nature. So, but we do find, at least recently, there has been some news about this, that people have found galaxies which have no dark matter in them. So, which is kind of a suggestion that maybe you have to have an extra field or extra matter to really explain dark matter. Okay, so that's what that is. Yeah, so another motivation, let's say, which is that MOND, which is, I don't know whether you have heard of MOND. MOND stands for Modified Newtonian Dynamics, which is just, it's a really ugly theory in the sense that it just takes F equals ma and modifies the a up the power of a. But it turns out that by modifying it just once, they can fit the rotation curves of a tremendous number of galaxies. A tremendous number may be too much, but a lot of galaxies. And strikingly well. Like some of them are surprisingly good fits. So it is not very clear to me, and I'm not going to offer any explanation why this fit actually works, but at least it is a motivation to consider why exactly MOND works so well. And I think that's a question maybe worth asking. So, and the most natural way to understand, one would imagine that MOND has to be some kind of a Newtonian or a classical limit of some underlying covariant theory. And if that is the case, So what is it that makes Mond work reasonably well in at least some of the, quite well in at least some of the cases? So that's one of the questions. And the way I kind of look at it is that it is known, it is completely well known that instead of changing Newtonian dynamics, you can also think of Mond as a statement that Newton's potential, the gravitational potential, changes form when the accelerations are very small. Okay, so this is instead of saying that the dynamical laws are changing, you can also reinterpret that as a statement that the field theory is changing, and that is something.
Sorry, I don't know anything. So Mond is a statement what? That F is equal to ma plus an inverse power of a?
No, so the power of a is a function that interpolates between 1 and 2.
So F could be equal to ma squared?
Yeah.
Then if you have like bigger galaxies, shouldn't that become less important? Oh.
No, but so, I didn't understand.
I'm trying to understand why it doesn't go the wrong way. If you have, so F is equal to,
I mean, it works. So, I mean, yeah, so.
Equal to ma squared or something.
Yeah, that's right. Yeah, so it goes from, it interpolates, it changes, yeah, basically that. And it works. So what you want is to fit the rotation curves, right? So yeah.
With some constant to make it.
But the interesting point about it is that there is essentially only one scale that they introduce. So that's what makes it somewhat interesting. So they're not trying to fit it differently for different galaxies. They just fit it once and it fits for a lot of galaxies. Yeah, something like that. So if once they do that, it becomes like, it's yeah. So which is, I mean, it's absolutely, it's a completely, I'm not recommending Mond at any level, but I'm saying that it's an observational fact that it seems to, I mean, you should see their, Wikipedia page, Wikipedia or Scholarpedia page, and some of the plots are quite striking. Like it's a very intricate plot of rotation curves and it seems to work very well. So with just one parameter, it is pretty impressive. But anyway, so, I mean, that's just motivation. I'm not really going to have to say anything about it. So, yeah, so this is what that is. So if one adopts the point of view that Mond should be viewed not as modifying dynamics, but as modifying field theory, then it is reasonable that you're, and field theory basically means Newtonian potential at some level, and if you are changing the Newtonian potential far away, stands to reason that maybe what you should modify is the connection. So that's one reason why I thought of it maybe, but it's, I'm not really claiming that this is really immediately explained in some way or another. So in any event, so let's get into what this is about. So the basic idea is that, so this is the standard Levi-Civita connection that is used in general relativity. And what we do is, instead of looking at that, we just add an extra piece, a tensor here, and this delta we treat as a background. That's basically all that is. So, and if you do that, typically what people do when they have a different connection from Levi-Civita, what they typically do is that they treat this whole thing as an independent field. So, and if you treat it as an independent field and vary equations of motion and so on, then you end up finding standard general relativity where gamma gets determined as a Levi-Civita connection. When you vary gamma as this thing. But here instead, what we are doing is we are going to treat that. We are going to add a tensor field, which is we're going to add a tensor field which is this delta, and we call this the Dhar connection. And this general connection can always be broken down in this way because the difference between any two connections is always a tensor. So this is, in some sense, this is the most general connection that we can have. So, and then you just write down Einstein's equations, Einstein-Hilbert-Lagrangian, and because delta is a background, note that now this is a functional of delta, and I don't have anything to say about it really. I'm just going to put it in by hand. So, so this connection, so this is the form of our action. The matter piece can have various things inside it, but this is the thing that we'll focus on for now. And this connection, the Ricci tensor is, so the thing that will be somewhat crucial for us, a technical fact, is that the Riemann tensor is only dependent on the connection and not on the metric in any direct way. So, and if you expand that, you find that this can be written in this way. Just one algebraic trivial fact again. And you do this, you find that this is the standard Ricci tensor, and there's an extra piece which is some connection like this. Some object which is made of these derivatives. And here the covariant derivatives that show up here are the Riemannian or the Levi-Civita covariant derivatives, and you find that this is the extra piece that shows up in your action. And the important thing about this piece here is that this turns out to be a total derivative. So that's what makes some sort of algebraic simplification for our what we do. So this whole thing, if you multiply it by the root g and all that, it basically becomes a total derivative. And what you end up finding is that this is your action now. Okay, so where this whole thing is what I'm calling this.
Excuse me?
Yeah.
And torsion is 0 in your approach,
Yeah,
right?
yeah. So I'm setting torsion to, so the thing that I'm adding is symmetric part. I'm not adding any torsion. So torsion has been explored before, and it can be of some interest, but it won't be necessary to make my point. It can be added if necessary. Yeah. Yeah, I am giving up metric compatibility. So and I'll have to make sure that things are fine. Yeah, the connection is no longer metric compatible. So so this is the extra piece that I get, and this is that particular piece. And note that the rest of the stuff is just standard Einstein gravity. There is nothing else has happened, which is kind of surprising because things could have gotten messy if this thing was not a total derivative. So in any event, yeah, so we are ignoring some boundary terms. I don't think it matters, but we are doing that anyway. So then you have, so if you vary that with respect to the metric, this action that I wrote down here, so then you find that this is your form of your equations of motion. And there is an extra piece TAB that is sitting here, which obviously we will interpret at some point as some kind of dark stuff. So this is just the matter stress tensor. And this TAB that comes up here is defined in terms of this T tilde that I talked about here as a stress tensor here. And the two points that I want to emphasize here is that it's symmetric in the two indices, and it's covariantly conserved with respect to the metric. It is not covariantly conserved with respect to the, it is not, the point is that it is conserved with respect to the metric itself and not covariantized with the full connection. Okay? Yeah.
This delta has nothing to do with the other terms, right? So you basically just have Einstein gravity
plus some random stuff, some quadratic piece with no kinetic terms, nothing. So it's like I am, yeah.
But you could just have added some tensor, GABT. You didn't even need to add.
No, but the thing is that my covariant derivatives on the fields, my interpretation of this object is as the connection. So my covariant derivatives acting on fields are still going to act with these guys, which will have a delta in them.
But in your LM, you're going to have delta is going to be sitting inside LM?
Yes.
Oh, I see. But I see.
But the point is that there are a couple of questions that one has to ask. One of them is, for instance, that let me get there. So it might not be. So let's I'll probably address some of your questions. More if you have, you can ask me.
Nice one. So are we going to vary delta?
No. So I'm not going to do anything with delta. I have no theory for delta. This is just a.
So there's no equation of motion for delta?
There's no equation of motion for delta. It's a background field. So if I want to have a theory for it, it's basically a theory for dark matter. That's what it is. But I'm just saying that instead of there is, what I'm saying is basically that you can, what I said earlier, which is that you can reinterpret the question of stress tensor in terms of a background connection. So that's really what I'm saying.
Eventually it has to be determined.
That's right. But if coming up with a theory for a connection is much harder than coming up with a theory for things which are, most of the things that we are used to are Lorentz invariant. Like all the things that we do is we do Lorentz invariant stuff and then couple it to metric in some way and move things around, etc. But this is a theory for the connection it's somehow much more deeply classical, I feel, than,
But I guess the idea is eventually it would be composite.
Yeah,
I mean, if you just take...
One could. We have some toy models of this type, and some of them actually turn out to be theories which are related to standard ones and so on.
I mean, I guess the idea is not to take delta as a fundamental... If you take delta as a fundamental field, you're doing Palatini gravity. And I guess you don't want to do that.
No, I'm not doing Palatini gravity because I'm... Are you saying that if I treat delta as just as a field at some kind of something like that?
Then it's a change of variables from Palatini gravity.
That's absolutely right. So if I just do delta and I'm varying with respect to delta, then there is nothing interesting. That's right. So I would like to have it, but so the reason why I like this particular, let's say, presentation is because where is it? Yeah. So this guy. So this is a tensor, and I can give it background values in some meaningful way. So yeah.
Excuse me, does it contribute to covariant derivatives on the metric?
Yes, it does. It contributes to covariant derivatives. Yeah, that's why I'm calling it a connection. Because it really is part of the connection. It does contribute to covariant derivatives, and so that's something that I'll have to be worried about. So, yeah. Right. See, the point is that, so let me emphasize this point that I said here. So, where was it? So, note that the stress tensor that, as I was saying, the stress tensor that we use for dark matter in cosmology, all it really does is it has an equation of state, and then it basically just follows covariant conservation of stress tensor. That's really how it really evolves. So, it's not that we have, that's really all you need to fit all data. I'm not saying that you ultimately would not want to have a theory which is a microscopic theory for the T mu nu, but I'm saying that roughly this is on the same footing. There is I don't have a particular theory for it, but I'm saying that it's really like a prescription for a stress tensor. It's somehow on the equal, this thing. You still have a question or? Okay. All right.
I haven't understood why it's conserved.
Huh?
I haven't understood why it's conserved.
Because it's a diffeomorphism invariant theory. It's a diffeomorphism invariant theory, and this is a metric equation of motion. That's it.
It's not just adding this. This T tilde AB is not conserved. It's this guy which is conserved.
It's TAB is conserved.
I
That's
see.
correct.
So T tilde
TAB
AB
is the thing that is sourcing this.
I see. But for now, in the action, you could just have added some term root minus GT tilde AB GAB without explaining the source of T tilde AB, and it would have given you the same thing, except the delta would not have entered the covariant derivative.
That's right, but that's a big difference. That's something that I have to be worried about. So also, it somehow changes the philosophy, right? It's not just that. It kind of changes the philosophy in the sense that, if you're just adding a delta mu nu, it is more like, it's not affecting any notion of parallel transport, for instance. So these things will change here. The metric covariant derivative. That's actually a very crucial point. And that's what will let me get away with hopefully get away with various things. So this is an important point. So you can stare at it long enough if you want, if you're not convinced. Because the point is that this really, so the claim is that if it is a diffinvariant theory and if it's a metric equation of motion, this has to be true. So
if this delta is a background field,
correct.
You have to specify its value in a way that respects diff invariance. So you cannot just say it's some specific function of the coordinates. So you have to say it really in a diff invariant way what its background value. So I guess you're going to explain next.
No, I mean,
what its background value is.
Maybe that's a good question. I haven't fully understood that question, but so.
I mean, normally the value would be determined by some equation of motion, but here you don't want to put equation of motion for it. So you have to fix some coordinate or some coordinate system and say that in this coordinate system it takes that value.
I am not going to do any of that. But so I think that, that's actually.
But if you have to fix a coordinate system to say what value it has, then you're breaking diff.
That's right. So then I think. What I will do is the statements that I'll make specifically with respect to lambda CDM would be within the context of FRW. So this is the coordinate system that I'll work with. So but that's actually an interesting question in the sense of there is actually a coordinate dependence, and how would you make the whole thing diff invariant is what you're asking. But on the other hand, maybe the whole thing, if you have a microscopic theory for the connection, maybe diff invariance is not what you would want at the end of the day. So it's a little bit of a.
Well, I mean, I think one answer is just that it's going to be a composite. That someday when there's a microscopic theory, delta will be written down in terms of some other variables and the whole thing will be diff invariant. Ultimately, it's not that ultimately it is God-given in terms of some coordinates. It's just determined in some degree, in terms of some degrees of freedom that we don't care about here.
Right. So it's like, even in a diff invariant theory, you can have the idea of a background field. So, so of course, how do you, in a full theory, of course, you have to integrate over everything, but at least at the level of, we know that there are background fields living here. So, at least. So, but that's a good question. I think I should think about that more. So, so now we'll just say some minor things, which is that, these are trivial facts again. So it is straightforward to argue that this type of a stress tensor indeed can reproduce a standard fluid stress tensor in cosmology and particle physics. A minor check in some sense, which is because, if you have an object delta which you can use to construct a T, you don't, generically you might expect that you can always manage to construct the right one. So here, so the way we will do it is that in standard fluid cosmology, we can motivate the existence of this stress tensor to have this form, just essentially by going to the co-moving frame and demanding that the symmetries are satisfied. So that's one way in which we can get to this DAB form. So P and rho will have to be scalars, and that's it. And we can apply the same thing in the co-moving frame for this Dhar connection, and then this object, this is the form that the most general form that you can have. And the question is whether if for instance, if you set alpha equal to 0, and if you only had beta and gamma, for instance, you won't be able to reproduce this. So it's not. So you do get some constraints from that. So anyway, so if you use delta to construct this dark stress tensor, then you find that the object that you have, so the equations that you have to satisfy are these. And then since there are 3 scalar fields on this Dhar connection thing, and there are only 2 in the stress tensor, one might expect that one might expect that it will have solutions. But the question is whether they are always real, etc., etc. And we can actually plot these things, and we have some plots. I haven't put them here, so you can explicitly show that there do exist like whole regions of parameter space where these things are completely well defined and everything. So this includes various, in various contexts, people use various models of dark matter. For instance, in some contexts they use dust. Some contexts, so you need cosmological constant. And I'm not even really saying that cosmological constant should really be put in this. I'm just observing that there can be a stress tensor, and this is the lambda CDM stress tensor, and all of these things can be realized using these if one wishes. So that's one thing. And so the question is, so that's basically the basic story, and we have some other things trying to find composite theory for this and various other kinds of things. We have various things like that we can try, but the thing that I would like to emphasize now is that what is the catch? Why is it that, this seems like a completely obvious thing that people have tried like 100 years ago, but why is it that, it seems to have not been looked at all? That I find very strange. And so I think one reason for that one reason for that I suspect is that if parallel transport and covariant derivatives are going to affect all the tests of general relativity, including equivalent principle, all the other detailed tests will be affected. And in other words, one cannot just declare that the Dhar connection is just another tensor field, and therefore the test of general relativity will be fine. So you can't just declare that, because parallel transport is going to be affected, so one has to be careful. So it is indeed a tensor field, but it could affect local parallelism. And so the weird choice of the connection will basically destroy the principle of equivalence, and that's the price that one has to pay if we have to, add this extra piece in the stress tensor. So in particular, the geodesic equation is absolutely essential for even detailed tests of general relativity. So, is there a question? The post-Newtonian approximation, which is thoroughly tested at this point, it really requires matter sources to move along geodesics. And this binary pulsar test of gravitational waves, all of that uses post-Newtonian tests in great detail, and it has been thoroughly tested, which means that we do need to keep it in place. And so for that, we really need the geodesic approximation, to be that of metric. And the question is, I think this is the reason why people have not paid attention to this at all, because I've seen some papers where they make statements of this kind, but I suspect that is the case. But I think that this is actually a misleading kind of a point, for the reasons that I think, you can tell me if you agree with me. So the reason for that, why I think it is not a particularly important point, is because in a theory, to decide whether your parallel transport of, if your geodesics are that of metric or the connection, is a thing that the theory should tell you. In your field theory, if you write down a field theory, it is in some limit of those field configurations that you would expect that you end up with a geodesic. And I think that in this context, we can argue that the geodesic limit of the field theory actually does lead to metric geodesics, which correspond to distance minimization and not affine parallelism. So in that sense, I think that I'll try to convince you that this is not a completely unreasonable statement in the next few slides. So that's the basic statement. So I hope that the statement is clear. So that even if your covariant derivative acting on fields is some generic connection, the claim is that in the geodesic limit, when you calculate the geodesic limit of those equations, you end up finding metric distance minimization as your physical notion of geodesic. So that's what we'll say. Yeah. Yeah.
So one way to derive the geodesic equation normally is if you imagine, for example, a scalar field, And okay, you can imagine a solution where the scalar field is very heavy, and then you take the limit of geometric optics of that, and you get.
I'll do that. And in fact, you will see that directly gives you the metric geodesic, even if there is an extra piece in the connection.
Yeah, exactly, because the action of a scalar field doesn't depend on this delta.
That's for gauge fields as well.
Yes,
so the light detection tests are all perfectly fine right away. That's
okay.
You're saying what I'm going to say in my next slide.
Okay.
So that I had the same question. How does LM change? Change. Only for
LM changes because there can be particles, like for instance fermions.
So it's only for fermions.
Fermions or anything. So for a scalar and for gauge fields, it won't change. So those are the ones that somehow, especially the gauge field, is what really matters for us. So the rest of the stuff, it might show up in various ways, but because of my statement, let me get there. So I think the answer to your question is still ahead of me. A couple of more slides, and then if I don't answer it, you can ask me. So your basic question is. Yeah, so maybe I should let you ask your question.
It's the same question, that the action looks exactly the same. So the geodesic approximation is not some deep principle, right? It's the fact that you take a lump of matter in the field theory, it'll move along a geodesic. I mean, it's not some external principle you have to put in. It's a conservation of stress.
You have to be able to derive that, any lump of matter is ultimately a configuration in field theory. But you have to be able to see that from field theory.
But it's the same action. This delta is not coupling to phi.
For instance, so only the scalar and the gauge field have deltas, not inside it, but the other things have.
So only fermions have.
No, I mean, if you want to add, various, whatever you want, I mean, some massive vector or something, it doesn't have to necessarily be a renormalizable theory.
But in our world, basically, you'll only be looking for fermion equations of motion, seeing whether that.
So, but I mean, but the point is more general. That's why I'm not, so quickly agreeing with you. The point is more general that whatever the connection might be inside the thing, it would not really matter to make the statement, as you will see, about the geodesic being a metric geodesic. So that's the point. I'll say that in a second.
Well, I mean, you have some freedom in how you write the scalar or gauge field. I mean, for example, a scalar you could write phi box phi for the Lagrangian, and now the connection would enter.
That's right. So, but I'm going to write.
Or you could write d phi squared, and then it wouldn't.
Right. I agree. So I don't have a good answer for that, but we are going to work with the standard one. Let's say. So, for instance, Maxwell's theory, I think maybe it's more natural to think of del mu f mu nu. I mean f mu nu instead of directly because that's the most natural thing. And f mu nu does not have any connection, and that's what I really need. I don't really care so much even about the scalar. The gauge field is where I really have to have f mu nu be there because f mu nu does not have any connection. So yeah, I mean scalar, like if you also the thing is that scalar, if I have a complicated potential, the connection will go in. So if complicated potential or complicated, some higher derivative term, whatever, it'll always have some stuff inside it. But the claim is that the things that I need are it's absolutely crucial for me that the Maxwell part has no connection, and the rest of the things, what will be crucial for me is that the del mu t mu nu that I calculate from it with the metric connection is 0. So those two things will be enough for me to make the claims that I make. Okay, so this is just kind of a recap of the questions that were just asked. So we'll motivate. So I'll say that we'll motivate these things because you can't really derive by arriving at particle geodesics in 3 different ways, starting from an underlying field theory. Since we cannot derive, so we will try to do it in 3 different ways and hope that somehow it is okay. So the first thing is what was just pointed out, which is that you try the Eikenal or WKB limit. It's a standard approach to get geodesics from field equations. And crucially, for photons and for scalar fields, the matter part of the action does not contain the connection at all. And the geodesic emerges purely from so if you take a geodesic limit, you automatically end up finding the metric geodesic, starting from Maxwell and Klein-Gordon-like equations. So the basic point there is that the Eikenal limit, their Eikenal limit parts are the same as in general relativity. And this is absolutely crucial, especially for photons, because light detection tests are, essentially the most important and basic tests of general relativity. And if the photon satisfies that, we have some hope that this might not all go to hell. So, another question? No. Okay, so that's basically the first comment I have to make about that is that. But the problem with the Eikenal limit, as I will say, is that this guarantees that the photons traverse the usual null geodesics of general relativity, but this approach is most clean in some sense when you have massless particles. So, because if you have a massive particle and you want to find the massive limit of the geodesic equation, you have to scale the mass as well. And that's not, I mean, you can do it mathematically, but it's not a very, compelling way to get to the final geodesic, because it doesn't really feel to me like it's a very physically motivated way of deriving particle trajectories. So for massive particles, whether they traverse geodesics is something that we would actually like to understand in a slightly broader, or at least maybe from a slightly different perspective than just WKB approach. Okay, so because the WKB approach is, yeah, I mean, as I said, it's scaling the mass doesn't seem like a very compelling way to do it. So a second argument that I'll use is one due to some general relativists, so the rest of all the couple of comments that I have, all of them are, results in general relativity. Maybe some of this is probably somewhat better known than the one that I'll use next. So this is a set of equations written by Papapetrou and Dixon, and they showed basically, so their idea was that you start with the stress tensor configuration in space-time, and then they tried to find out how the multipole moments of that stress tensor configuration evolve with time, starting from the fact that del mu t mu nu is 0. So you have del mu t mu nu is 0, and then you use the stress tensor configuration and try to see how it evolves into the future, and that tells us, so essentially by putting in covariant conservation of the stress tensor as the only input, they were trying to derive particle motion. So what we will take from their work is basically that we'll just look at the center of mass contribution of that. So we have this T mu nu distribution. We just look at the center of mass contribution of that, and we find that so the fact that they find that the center of mass actually moves along the geodesic. Okay? So the metric geodesic. And that argument we can check we can go through their calculation and check that none of that depends on anything. It just directly you can derive starting from del mu t mu nu, and you see that the metric geodesy comes out of it, without any kind of problem. Yeah.
How do you define the center of mass in a curved space?
So T mu nu x mu integral. So there is a bit of stuff that I'm not telling you.
Oh.
So there is like
it's not covariant.
X times T, T mu nu, whatever.
So it's not covariant.
It's not covariant. Yes, that's right. Yeah. So yeah, but I mean, I think that to the extent, this is a very well-believed statement by general relativists. Let me just say that it's not covariant. I agree, but the final result is it's reasonable and it is So anyway, I don't have a proof. I'm not claiming that there's a proof. So yeah, so that's true. So the statement this satisfies the covariant with respect to the metric, and this is the center of mass trajectory you can think of as a geodesy coming from the metric. Yeah. So their goal was to derive a multipole expansion for motion of matter in general relativity, starting by only putting in del mu t mu nu as the input, and so we are just using the monopole part. I just mentioned it. We have checked that their calculation goes through self-consistently as long as the stress tensor is covariant conservative metric. So this is true for the stress tensor, even if the Dhar connection is turned on, and that's the main point. So the essential point on which everything seems to hinge is the fact that del mu t mu nu with the metric the metric covariant derivative is 0, even if t mu nu contains things which are have other pieces in the connection. So yeah, so this is this approach has one advantage, which is that it's true both for massless and massive trajectories, and we are not limited to our or not just light trajectories. And this is important because we do need the geodesics for massive particles as well in order to survive in this theory if we want to reproduce the success of general relativity. So the success of general relativity are crucially reliant, as I emphasized, on both the geodesics of massless as well as massive particles, and so we need that. Okay. So now I come to my third and final argument. We'll present is a theorem due to Geroch and Jang. And so there the statement is that, so here one of the things that is problematic in some sense is that they're not really looking at a finite particle-like configuration. They're looking at the monopole component of a distribution. So it's somewhat reasonable to believe that that's an approximation for a particle, but it's not quite the same thing in the sense that it can be any distribution. They are computing the center of mass motion. I mean, it's reasonable, but it's not. We would like to have maybe one more piece of evidence to believe that this is not so bad. So the third argument that I'm using is one due to Geroch and Jang, and the claim here is that, like, if you have a space-time which is generic space-time, and then there is a curve on the space-time, and around the curve there is some region in which you have a stress tensor. Okay, so there is a stress tensor on that curve. So let me just draw a quick picture. So there is a curve in space-time, and you have a small tube or whatever around it, and this is the region O, and there is stress tensor is supported in that region. So if that is the case, and if you make these following assumptions, so this is the strongest of the assumptions, this idea that, so it's some dominant, powerful, some kind of, it's more than dominant. So it's some kind of strong energy condition. I haven't put it here, but I can find it for you. So this, and the second statement is what we want, which is that it is covariantly conserved. And the third statement is that it is supported around the curve. And the final assumption is that it is just not just empty. DAB is not empty. There is something here. And within these assumptions, then they show that because this energy condition is actually a time-like energy condition, they show that this trajectory must be time-like. Time-like and geodesic. So this is a pretty surprising theorem, but it is true, and it is true according to, so the proof is, I have not fully understood the proof, but it is, we hope to understand it in the near future. So this has been, but it seems like Geroch is a reasonable person, so I assume that the proof is correct. So anyway, so it is possible to check that the theorem does not rely on the choice of connection. This we have managed to check, even though we haven't fully understood the proof. We can go through the proof sufficiently well that we can argue that the statement that they need are just these and the covariant conservation, and none of the things ever depend on any choice of connection. So this statement is, so this is the third argument. So yeah, so that's basically the final one. And yeah, so the strength of this Geroch-Jang theorem over the Papapetrou thing that I was talking about is that it formalizes our idea of a point particle instead of just looking at center of mass motion. Okay, so that's one good thing about it. But so yeah, by looking at infinitesimal neighborhoods of curves. The weakness is that it requires an energy condition. Okay, so energy conditions, yeah, I mean, even in standard general relativity, I think it is probably not that easily understood. So this is the price that we pay. But in any event, we will take these facts collectively as showing that macroscopic test particles and light traverse metric geodesics as expected in general relativity, even when there is a dark connection. So this is our conclusion, and which seems to suggest that having a connection, having a background connection, really very well could be, one source of one piece in the stress tensor. Okay, so there's too many of them. So let me conclude by saying that, so basically what this is the conclusion. We have argued that the background non-Riemannian piece in the affine connection might be indistinguishable from dark matter. And according to present-day tests, one of our goals in doing this was to see how stringently gravity modification is ruled out as an approach to dark matter. I mean, I don't know whether one should really call it gravity modification, but it does look a little bit more like gravity modification than usual attempts at dark matter. And it seems to, so I would say that the answer seems to be not very strongly. And so one of the things, so I haven't shown you some of the things that we have done. So one of the things we have not emphasized, which I think might be interesting, is that for fermionic particles, the dark connection will give rise to a 3-point interaction piece in the Lagrangian. And this will in principle be about the same strength as dark matter direct detection tests. And I don't, yeah, and it will be interesting to see if it has any detectable signatures. So I think I have stopped a little bit ahead of time. So thank you.
So can you explain what happens to fermions in some more detail?
Yeah, so we are still working on it. Yeah, so it's just that, the connection gets an extra piece. So that basically looks like a 3-point vertex. That's really the summary. So, and that 3-point vertex can, because the connection has to be dark matter strength, I don't think it will violate equivalence principle and things like that. So I think it will basically show up as a test for, it will have the same strength as a direct detection experiment. That's what I think. So maybe as a fifth force or something like that, but yeah. But I think it is within bounds, I suspect. But I don't want to make too strong a statement there, but yeah.
Why won't it violate the equivalence principle? You have an additional interaction between fermions that you do not have between other particles.
Right, but
you drop a fermion, you drop something which has,
But I don't think that has been tested, right? All the tests in where we drop a massive particle of that kind, I don't think a fermion has been dropped and that test has not been made. So, yeah, so that's the sense in which we are saying that.
No, I don't.
So in principle, yeah.
No, I think those tests have been done, right? Because you can drop particles with different numbers of different ratios of fermions to bosons. I mean, that's the whole these Eötvös tests are precisely that, right?
Which one?
I mean, all the old Eötvös experiments, and I'm sure there are newer ones. I mean, you drop like gold and nickel or whatever, which have different amounts of the mass in each of them. Some of the mass comes from fermions. Just the
but see, the thing that it is coupling to is also dark matter strength, in the sense that it is going to be, so in solar system level it is some 10 to the minus something. So so if it is just something that affected it at some reasonable strength, I would imagine that to be the case.
These things are very accurately tested, right?
Really?
Most of mass comes from the gluons, that's right. And so, but there's some amount of it which comes from the fermions. So you're right that maybe a few percent comes from the fermions, and so
much less than that. But you're right. Maybe there's a
how much of it comes from the fermions? How much of it comes from the bare fermionic mass? I would have thought a few. Isn't it a few percent?
Okay.
A typical atom, I would have thought a few percent.
Okay, yeah, maybe, yeah.
So a few percent comes from the fermions.
So what is the name of the experiment?
I mean, it's just the test of the equivalence principle. This is precisely what they're testing.
I've looked at some of them, but I didn't find anything which seemed sufficiently so you're basically saying that
because of what he's saying, most of the energy is coming from the QCD.
That's what he said.
So now there's the only thing you're interested in is what is the ratio of the mass that's coming from the gauge bosons, which is not affected, and the mass that's coming from the fermions, which is affected. And that ratio is, I think, different in different in different nuclei, because it's probably different in a proton and neutron.
Yeah.
So and that's what they're testing. They're testing if protons and neutrons are attracted at the same rate, and they're attracted at the same rate very accurately. So what you're saying is true.
Let me just say that I'll look at it.
Okay, but that, yeah.
But I mean, it's on the face of it, he's also got a tiny number on his side, right? I mean, because the density in on Earth of dark matter is extremely small.
And I think that it is. I've checked that the Lorentz violation tests from dark matter are the Lorentz violation bounds are close to the dark matter bounds. So the amount of dark matter around in our vicinity. So there are numbers are really small. So I look at it, but
the neutrons and protons are attracted at the same rate. That's
I understand.
So I thought they did that very accurately. But you're saying,
well, very accurately for gravitational experiments is sometimes not very accurately, for other.
Okay, it's fine, but I think it's worth checking.
Yeah.
No, absolutely.
But it's not
that's
ridiculous.
One of the reasons why I did not emphasize it too much. So I just left it at one statement at the end so that somebody would pick on it. But
but I mean, I'm slightly confused about. I mean, if you think in terms of quarks and gluons, I mean, this difference between bosons and fermions seems to depend very much on what scale you're looking at. I mean, I could say the neutrons and protons are fermions.
Right. No, I agree.
So now I'm confused about.
So I don't really know how to think about the a fundamental field theory Lagrangian. How should one couple it to gravity? I'm not very clear on that. So because if you're really coupling, or should I couple the standard model to the general relativity, or should I couple? I mean, I think it as you're saying, it really depends on the scale. So I'm not. I mean, I don't have anything intelligent to add to what you just said. But if you have any comments, actually, that'll be good.
Maybe a comment on this. So, I mean, in general field theory, you will just list all possible couplings you can write, and then in the general field theory, for example, if you have a scalar field, you can actually write a term that has a single derivative on the scalar field times this delta. You take a trace of it. There's one index you can track with the derivative. So there is, in principle, a free parameter that allows you to couple a scalar field to this delta.
Yeah.
And so if you think about this like this, you have all these parameters you can play with. But in effective field theory, you will the ones that are that has the least mass dimension will be the most important ones. And I think with this power counting, you can figure out.
Well, in fact, that term is the difference between phi box phi and del phi squared.
Yeah.
So you should, in principle, include it.
Yeah.
So you're talking about this Lorentz invariant, the Lorentz violating standard model. Those kind of corrections are what you're talking about. I didn't quite catch what you're saying.
Let's keep talking.
So no, it's fine.
They're not Lorentz violating. I mean, if the function is background.
Yeah.
Just add a mass term to the fermions?
No. Yes, that's correct.
It's just a mass term?
Yes. So psi bar, gamma mu, yeah, that's right.
Mass term is not coming from the Higgs.
Yeah, that's right. This is a new theory.
Maybe one last question. So you showed this parameterization of this additional stress tensor from delta in the case of a FRW metric. Have you actually tried to solve for the Einstein equation with that corrected thing to see how the FRW gets changed?
I didn't quite understand what you're saying. So because the only thing I really need to do is that, so the only equation that I need to solve is the one that is Einstein's equation, because T mu nu does not have any, I'm not solving anything for T mu nu, right? Del mu T mu nu is automatically 0.
Yeah.
So I don't have any more equations to solve. I think what you're probably saying is that I need.
Well, I'm wondering really if that's true, if that d mu T mu nu is 0. But okay, let's discuss.
Del mu T mu nu is 0.
Okay, let's discuss after.
Yeah. So there will be a condition. Essentially, I think I know what you're saying, because the different parameters that I put in, rho, gamma, those three things should satisfy a condition. That's what you're saying, right? Yeah, but the point is that the equation of motion I'm imposing is not at the level of the Dhar connection. I'm doing it at the level of the stress tensor, which automates it basically. Because that is automatically guaranteed to, as long as that satisfies the del mu T mu nu in the FRW background, this is automatic. So yeah, I mean, maybe we can discuss, but yeah. Yeah.
So it's true the del mu, but so now the relationship between delta and T mu nu is not so trivial. So you need to
Delta and T mu nu, yeah.
And this T, because there's some combination, right? I see, but you have no constraints on delta. So just given a T mu nu, you can always find a delta that'll reproduce the T mu nu.
No. So this is what I was saying, that if
it has to be real.
Specific T mu nu that I need for FRW, I need to take there'll be a space of parameters from where it will come. The point, in answering his question, what I was saying was that whatever they might be, the equation of motion that I have to satisfy is coming only at the level of the stress tensor. So as long as I satisfy that equation of motion, then this is automated.
I know, but there's some dark matter halo which people have calculated. And you have to see that comes
numerical simulations. Yeah.
But there might be, just assuming that delta is real, might also give you some constraints on what possible stress tensors you can get from delta.
Yeah.
And are you sure that none of those are violated?
What is violated?
Just the fact that delta is real may tell you that not all stress tensors can be.
Right. That's what I just did. That's what I was telling you.
So you got some fluid and so on, right?
Yeah. So if to get the lambda CDM stress tensor, I need to have, I'm not allowed to have every possible delta. And that's what I say. I didn't show you the plot, but I can do that. So if I look at the parameter space where it's there is a finite, huge, a finite fraction of the phase space of these things, phase space or the configuration space of these things, which is allowed by this thing. That's why I didn't put the plot, but I mentioned it. So yeah.
So I want to understand this difference in adding this, as a part of the connection versus adding just this as a part of the term in the Lagrangian. It will be like a cosmological constant, right? So adding this as a part of the connection only gives you some sort of interaction, as you said, between the fermions and this.
Right.
Yes. So if you add this just as a cosmological constant term and not as a part of the connection, it won't interact with the fermions as a fifth force or whatever, but it will enter that stress energy tensor.
So no, but maybe you should ask your question. So I think that
So I wanted to the way this delta appeared in your action was via this T tilde mu nu, right? It was basically root over minus G mu nu T tilde mu nu.
Yeah.
So if I
It's not T tilde, so the thing I added was T, T tilde,
T tilde mu
my notation, but
yeah.
the T tilde was the thing that was getting added to the action, and T was the thing that, the curly T was the thing that finally turned up as a stress tensor.
Okay.
Yeah, so
it's, so if I think of G mu nu, T tilde mu nu as my cosmological constant, so what you're saying
G mu nu, T tilde, yeah.
G mu nu, T tilde mu nu, it's the cosmological constant would enter as root over minus G times lambda.
Right, so the point is that whatever the stress tensor might be, I can.
Yeah, it's a cosmology. Yeah.
So here, for instance, so if I can make this. So if I choose my deltas to be appropriate, then I can make the lambda to be a constant. right?
Yeah.
So if I want, but I don't know whether cosmological constant should be added to this. I kind of try to think of this as dark matter.
Okay, I mean, let us not think of it as a cosmological constant, but as some background field that
Right.
you have.
Yeah.
If it,
But then
if
I
it
don't have a
enters,
theory for the background field.
if it enters a Lagrangian like this and not in the connection, then what's wrong?
If it enters.
If you don't modify the connection, but rather put it by hand in the Lagrangian.
Yeah, I mean, there is nothing wrong with it. I mean, you can do it. I mean, yeah. So I'm saying that, but this gives us an intuitive picture, right? Then there is a, so instead of like, you can add a stress tensor by hand to this, but that gives you really no explanatory power at all. So, but here I guess the point is that, when you think of it as a connection, it gives you some, I think I learned something by doing it. So that's non-trivial.
Yeah, if like there is a difference between if it enters the connection and not as a separate term in the Lagrangian is specifically what you told us, that interaction with the fermions will be some extra feature that you will have.
Right, that's right. So if I just add it, I mean, I get what I put, I precisely get what I put in. Here, I have to pay some price here and there possibly, but I think that, overall it seems more interesting than what I thought it would initially be. So that's the bottom line. So let me just to understand. So your statement is basically that why don't we introduce a cosmological constant as a background field, just as a background field? Yeah, so that you can do. So yeah, I mean, but then it's just like there's nothing. You just that's all you have.
Okay, so thank you. That's a nice, fun note to conclude. So guys, here. So let me just end by I think this is the end of our 2-week workshop. Thank you, everyone.